Good morning. It's the physics video lecture once again. This is Physics 4B video lecture 12. And I'll begin with some announcements. We have an SI leader. So here we go, announcements. So the supplemental instruction by Dan Bautista and I'll give his hours right here. So the SI schedule, and then there's also office hours. So we have Tuesdays and Fridays. Tuesdays 5:30 to 7:30 p.m. and Fridays 10 to 11:30 a.m. And the office hours Monday and Wednesday 10 to 11:30 a.m. and 5:30 to 7:30 p.m. So there you have a lot of opportunity to get some added perspective, and you can ask about the homework, discussion of the quizzes, things like that, and just the lecture material. The next point was the quiz that we took, quiz number 1, and I'll review what we had there. It was an ideal gas problem. So let's see here. Quiz number 1, the ideal gas problem. And the idea was that we had a bubble being released by a submarine and it reaches the surface and it expands in volume. So down here we had R1, the radius of the bubble, and up here we had R2 was some constant times R1. Okay, so that constant was different for everybody. And the question is, what is the depth? Given that we were, the bubble had expanded in radius and of course in volume. So what do we have? We have P1 V1 equals P2 V2 because the temperature had been stated as being uniform. Okay. And P1 would be the atmospheric pressure plus rho GH, and the volume sub 1 would have been 4/3 pi R1 cubed. Now, up at the surface here, we again have the atmospheric pressure, and the volume is 4/3 pi. Now, the new radius is R sub 2, so we can write A times R sub 1 cubed. And everything, or a lot, is going to cancel here. 4/3 pi R1 cubed is going to cancel. We're just going to have A cubed on the right side here. So we end up with density GH is equal to the atmospheric pressure. I've already subtracted, well, I'm about to subtract off. So just looking at the right side, atmospheric pressure A cubed minus 1, okay. 4/3 pi R1 cubed canceled from both sides, so we had P atmosphere A cubed, brought it over from this side, minus 1, and now we'll just divide by density of water times G, and we'll have H. So H was equal to the atmospheric pressure, A cubed minus 1, divided by density of water times G. And the program I'm using, I set it for a 3% accuracy. So you can't round too drastically, but 3% is pretty generous in a thing like this. Good, so that's how it went. Let me know if you have any more questions on that. Good, moving right along. So now we're back to talking about Gauss's law, which is just a great moment in electricity. So first I'll just write it down again. Gauss's law. And that is that the electrical flux is equal to the enclosed charge divided by epsilon naught. So that's a pretty simple formulation. Now if you have some charge here, so there's Q, and it's enclosed by, I'll use another color, say it's enclosed by some non-spherical surface here. So the electrical flux is the surface integral, the flux integral, and I can make good on when I had said I'd get a little explanation of this. So imagine you just had a little bit of charge right there, and we know out here we have some, actually I want to make a point. It'd be better to talk about the area right down here. We would have an area element, dA. The field vector due to this charge is pointing in that direction. Okay. So this is my surface normal, the red one here. My field is like that. So there is an angle theta between them. And I could write delta phi would be, the flux here would be the field Q over 4 pi epsilon naught, just from that little red dot of field, okay? Q over 4 pi epsilon naught, r squared, that's my field. I should write here, L flux is E dot dA. Okay. So there's my field here. You can see I've got cosine of theta, so we're talking about a dot product. So for my dA there, I would have, it's going to be proportional to r squared cos theta. R squared cos theta, and then I'm going to have a d or delta omega, which is a element of spherical angle. So, and this r squared here is simply because you're a distance from r squared away, you're sweeping out a certain amount. Your distance r away, you're sweeping out a certain amount of area. So that's where the cancellation comes from. When you integrate all of this angle up, this integrates solid angle integrates to 4 pi, and that's where those cancellations come from. Your r squared, your 4 pi cancels out, and it's just whatever charge was enclosed. Okay. So yeah, that by way of justifying Gauss's law here. So what we were looking for was E dot n hat d area is equal to the enclosed charge over epsilon naught. Now generally, we're going to enclose the charge in an integral of density d volume. Charge density integrated over volume. Good. So we're going to do a couple more of these. These are kind of fun. So that was that formulation. Okay. And this is just for review. And this kind of gives justification for the Gauss's law thing. The way I justified it last time was actually just talking about a point mass and spherical symmetry, where of course it just falls into your lap as well. But it's really the same type of cancellation right here. Okay, so let's look at an example or two. So I will review the uniform spherical problem, or let's say I'll just review its result, and then we'll go into some other symmetries. So the example was uniform charge density. Density such that we have a sphere of radius r, and we wanted the field inside and the field outside. So that one I did. E inside was equal to the total charge, 4 pi epsilon naught r cubed, and then it was proportional to r. Okay, so it just grew linearly. And if I didn't take it to this step, I took it to the charge density step. Okay, but it's the same answer when the charge, when you're inside the sphere between 0 less than or equal to r less than or equal to capital R, you have this linear formula. Outside, 4 pi epsilon naught r squared. And as always in these spherical situations, the field is just radial. Okay, it's radial anywhere, whether or not you're inside or outside the sphere. So this is the one you want to review again, and the homework problems are applications of this idea that are even more interesting than this one. The graph, by the way, and this was for r greater than or equal to capital R. So yeah, you've got this linear growth, and you'll notice when lowercase is equal to capital R, you've got Q over capital R squared. Same here, okay? So that tells you that the graph is continuous, and it goes linearly up to a radius R, and then it decreases. Now the homework and the one that's to come didn't give us the uniform spherical charge density, but it gave us some function of R. And then your integral is not difficult though. All of these integrals are done with your volume element being 4 pi radius squared dr. So, you know, let me even add that to here. Well, no, that was, this was general. When they're spherically symmetric, then you can do what I just said. Let me go ahead and write that down now. Because we're going to do another one of those on the homework. In fact, while I'm at it, how about if I bring that up right now? So I intended to assign, at the end of class I'll probably repeat this, but I intended in chapter 22 a very interesting one. Yeah, this will be problem 73. What we're going to look at is a charge density So yeah, how about we just, as an example, this is a homework problem, good time to start talking about it, problem 73. I'll have to remember to assign it. So it's problem 73 of chapter 22. The idea is we're going to have a positive charge, namely a proton charge, at the origin, and surrounding it we're going to have a smeared out electron charge. And this is going to be an atomic model. Okay, so you got plus Q at the origin, and you've got minus Q all over the place, but spherically symmetric. Okay, so I'll write here minus Q. So that charge density is rho of R is equal to minus. Well, in fact, we'll leave the minus sign. They don't write it as a minus sign, do they? Yes, they do. Minus rho naught e to the minus 2R minus rho naught e to the minus 2R divided by A. So that's exponentially decaying, and this is actually chosen to be the Bohr radius of the hydrogen atom. So how do we deal with this? In this case, there is no finite R at which it vanishes and where we can do a construction like this, but rather it just goes out to infinity, but it decays exponentially, which is to say very rapidly at some point. So just to remind you guys, e to the minus x equals 1 right here, and then decays very rapidly. Okay. Here you have e to the minus 2R divided by A, so A sets the scale. Okay. So how do we get the charge? So Q enclosed is going to be this integral minus rho naught e to the minus 2R divided by A. And our volume element would be 4 pi r squared dr. Okay, 4 pi r squared dr, that's the volume element. And our integral would go from 0 to r, which means we have to call these r's r prime as integration variables. Okay. So this exponential is vastly more powerful than the r squared, so this is going to converge very nicely. And when you go out to infinity, for r goes to infinity, how much charge is enclosed? Well, 1 electron charge. Q enclosed equals Q electron. Call it E if you want. And since they're giving you a value for A, that allows you to determine what this rho sub 0 is, right? That'll be an unknown constant there. Okay, so that's an excellent problem, Gauss's law problem. Yeah. So let's see what's next. What's next is the linear charge distribution and Gauss's law. So next, linear charge distribution. So what we're going to have is a linear charge density. Let lambda, I'll just put it in square brackets, so lambda is charge per unit length, so that's, I'll write it in words, charge per length. Our units would be coulombs per meter, obviously. Okay. So it's a linear charge distribution, and say we have an infinite line charge infinite line charge, okay? And we want to know the field around the infinite line charge, okay? We go ahead and draw a Gaussian surface, as it's called. So we enclose a line charge centered on that cylinder there. I'll go ahead and say there's a length L, and there is, I'll use R for radius. So this is now the distance from the line charge. Okay. And then the question is, what's the direction of the field? Well, let's go ahead and write down Gauss's law first. So we'll be looking at E dot n hat dA, or just dot dA, n hat, the area is equal to the Q enclosed over epsilon naught. Okay. Closed surface integral. Now, because it's an infinite line charge, or we're close enough for it to be effectively infinite, the E field can only have a perpendicular component. Okay? Any parallel component to the line charge would be negated by a field vector from the other side. Okay? So any parallel components are symmetrically canceled, and you just take that as your origin for the moment. They're all canceled as you go out to infinity. So all that's left is a field vector that points away from the line charge perpendicular. Okay. And that means that there is no flux through the top or bottom of the cylinder. Okay. So this flux integral is just going to be E times the surface area, which is just 2 pi r times L. Okay, so it was the symmetry consideration that told us the direction of the E field. Okay. So the left side here, 2 pi r L, so I'll just put it here, a note, no flux at the ends, neither the top nor the bottom. Well, how much charge is enclosed? Okay. Well, we have charge per length times this length, capital L, so that would be lambda times L. L cancels from both sides. We're going to go ahead and obtain for our E field lambda over 2 pi epsilon naught r. What's important here is that we see that we have a 1 over r dependence as opposed to the original point charge 1 over r squared. So yeah, very important result. For you guys, for the homeworks though, we want to ask what would be the situation if we had a line charge, but it itself is on a cylindrical surface. Okay. So my next example, and there will be a homework problem of this type, is find E for a charged cylindrical shell. I'm thinking that's the one I decided on. Let me consult here. Yes, cylindrical shell. So we have one for a charged cylindrical shell. And okay, so it's infinitely long, but I don't have infinite boards, so let's just say we have, there's the cylindrical shell. In red, I'll have the axis that it's centered on. You're going to be able to show, because the charge is on the shell, that there is no field inside. Okay. Show E equals 0 for r less than, let's say the shell has a radius capital R. not sure what it is, but radius capital R. And then outside the shell, you'll be able to draw a similar conclusion to this. I may want to add even another one here of that same type. Let's consult the book. I'm going to add one. We're on a roll here. So once you've done the cylindrical shell, let's just keep on. Now, the next one will be a cylinder, okay, charge. So the next example, also homework, uniformly charged cylinder. Now the cylinder is not going to be infinitely long, so what they do is tell you to consider the field at the midpoint, and in a plane perpendicular to the midpoint, and then you can do the same symmetry arguments we did for the infinite shell to say that any non-radial components cancel each other. Okay. But yeah, you'll have a charge density. You'll have a volume charge density based on total charge per volume, but then for the line density within a cylindrical shell here, you'll have to construct the line density based on integrating up some sub volume of that cylinder. Okay, that should be a good progression. Okay, it's analogous to the spherical one, and you know what your basic result is. It's got the 1 over R form. On the inside though, who knows what we'll get? Okay, on the inside, I'll leave you guys in suspense, but you follow the analogous ideas, analogous steps to the spherical one that we did. Okay, so there's one more very important symmetry, and that is the infinite plane. So I'll leave that up here, talk about the infinite plane. Next, field of an infinite plane. Of a charged infinite plane. So how are we going to draw that? Well, we'll lend it a little bit of perspective, but basically there's the right side and the left side of this infinite plane of charge. Just go ahead and say it has a bunch of positive charge on it. And we already had an infinite plane when we had our disk the other day that we let radius go out to infinity. And what we had found was that close to the surface, there's a uniform field that is perpendicular to the plane and has a constant magnitude. So what we're going to do is draw a Gaussian surface of the pillbox variety. Let's see here. And on this side, like that. Okay. Okay. Here the idea is that the field vectors are perpendicular. There are no parallel components, and therefore Gauss's law tells us we're going to have integral E n hat d area Q enclosed over epsilon naught. Field of infinitely charged plane with sigma equals charge per area. Should have put that. Okay. And what we're going to have on the left side is E times A. And we have one area here and one on the other side. So we have times 2. The enclosed charge is going to be the charge density sigma charge per area times the area. Okay. But now we're talking about the area on the sheet of charge itself. So that only comes in here once. And we get E is equal to, the A cancels, we get sigma over 2 epsilon naught. That's a really important field that we'll make use of repeatedly in the course of the discussions. Okay. Perpendicular, and then there's its magnitude, sigma over 2 epsilon naught. Okay, let me consult my concept here. Where are we headed with this? Ah, yes. So what's the meaning of these infinite planes, infinite charge distributions, when we know they're not really infinite in real life? Okay. So what's the meaning of infinite objects? Let's start with the plane. And I had mentioned this earlier, if you're close enough to a flat object, it appears to be infinite to you. Okay. So even this whiteboard here, if you're only a millimeter away from it, then your field of view is completely dominated by that, and you could treat it as being infinite. As you go further and further away from it, it turns into a whiteboard here, and if you're a couple hundred yards away from it, it starts to look like a point. Okay, so that's the significance of all of these symmetries. You have to make use of your relative scale as to whether you're able to actually invoke those symmetries or not. So yeah, relative distance. So my whiteboard example is not a bad one. Okay. Whiteboard, say we start from a kilometer away. From 1 kilometer away, it's just a little white speck, so it's a point. As you approach it, it fills more and more of your field of view. Eventually, if you're a millimeter away from it, it just completely dominates, and it's effectively infinite. Okay. That's the meaning of all of these expressions there. Okay, good. There's that discussion. Let's see how we're doing time-wise. Okay, so our applications now, we're going to apply these ideas to conductors, and we'll be able to get a couple more conclusions here. So conductors versus non-conductors. And you'll notice the problems in the book will always be careful to specify that. In a conductor, charges move freely. I think I brought that up before. In a non-conductor or an insulator, charges are basically bound if you place charges on an insulator, the idea is they pretty much stay where you put them. If you place charge on a conductor, it can spread around freely. Okay, so charges are bound here. So that leads to different behaviors in terms of fields. So my example is a non-conductor. So we'll begin with a non-conductor. And we had talked about, so here's a non-conductor, and we put plus Q here. Okay. So what happens? In a non-conductor, you're going to get charge polarization locally. So since the plus here, you're going to get a sheet of negative being separated from positive, like this. Okay. So you get the charge polarization. If you have a conductor, on the other hand, and you do the same thing, because charge can move around freely. Okay, this lower picture doesn't know about the upper picture. So here we have plus Q. What's going to happen here with a conductor is your negative charge is going to attract, and your positive charge is going to repel. So there's a different picture there, okay, between the conductor and the non-conductor. And both of these examples were neutral to begin with. So you got this type of polarization here, you get a different kind here again. Neutral on neutral, right down here. Okay, so with that being said, let's look at the field in a conductor. So what do we say? They're free to move. Okay. So what about the field, E field in a conductor? Okay. So here's our conductor, it's a piece of metal, and the charges are free to move. So they're going to move around until, due to, say, inner processes of friction of some type, they will adopt an equilibrium position, and any motion of conducting charges will come to rest. So charges so they're inside a conductor. Charges will eventually come to rest. And yeah, you have to base it on some kind of friction, okay, which we'll justify more later. But yeah, if they come to rest, then by definition, there's no more net field inside the conductor. So if they come to rest, then E equals 0 inside the conductor. So that's the equilibrium argument. To rest, E equals 0, so I'll write equilibrium. Now we can, here I'll do this in a two-stepper, 1, 2. Now we can draw a Gaussian surface here. Okay, right, I just write it on the inside of the conductor. And if E is 0 there, then there's no net, identically equals 0, then there's no net charge inside. Okay. So then by Gauss, no net charge inside the conductor. So that's how the charges will arrange themselves. They will arrange themselves to achieve these two points, that the field is 0 inside the conductor and that there's no net charge in the conductor. So if you drop some charge on a conductor, it's going to have to end up staying on the surface. So that's for starters. What about if we have a charged conductor? So next, charged conductor. Now that we've found these two results here, and again we'll draw our blob of a charged conductor. So now we know we've put some surplus charge on it. Let's just say pluses. Okay, now the question is, we already know field inside, net charge 0. What about at the surface? So now we do a Gaussian element of the type we were just talking about. And that quickly tells us the E field. Namely, if you're close enough to the surface, they've got that argument I just had about being close enough, say, to the board. If you're close enough to the surface, it seems like a flat surface. For example, we're on the surface of Earth. It seems kind of flat to us, even though we know it's a sphere. Okay. So you're close enough, seems flat. There's your n hat. And you're going to have an E field. Okay, let's even write down Gauss's law again. So you're going to have E dot n hat d area Q enclosed over epsilon naught. This time, there is no flux on the other side of this thing because the E field was 0 inside. So you're just going to have E times A, not E times 2A, equal to Q enclosed over epsilon naught. And we know that that's sigma times A over epsilon naught. So the A cancels here, and we get, I'll write it right here in the middle. Here we go, right here. E is equal to sigma over epsilon naught. And the direction at the surface is normal. Okay. All right, normal. So that's a result that we'll meet up with again as well. You got the magnitude. Remember, on the sheet of charge, it was sigma over 2 epsilon naught. On the surface of a conductor, it's equal to sigma over epsilon naught. And again, we can also argue that it's normal, the field is normal, because if there were a tangential component, the free to move charges would move around and arrange themselves until that tangential component goes away, and then you'd have normal component again. Okay, as far as the material from the chapter, that's about as far as I was going to go. I'll write up the homework problems and maybe set them up a little bit more. Yeah, I think this is, yeah. Good, so let's send this up and see what this has to do with our homework problems. And we're looking at homework from the 12th lecture. I have written down here chapter 22, problems 48, 51, 48, 51, 61 and 62, and 73. And now let me consult the book and see what each of these was all about. Okay, so 48 was the field of a charged cylindrical shell, and 51 is the solid cylindrical charge. Actually, 50 would be good to do too. Maybe I'll change my mind on this. Hold on. Yeah, let's do 50 instead of 51. That's the more standard progression of ideas. Okay. So for this one, you have a uniform infinite cylinder. Here, I'll get rid of this. And you can just do the fully analogous calculation, fully analogous to our spherical discussion. Okay. So for problem 50, infinite uniformly charged cylinder. Because it's infinite, there are no end effects, and you've got the radially outward direction of the field. Your Gaussian surface for being inside the cylinder is like, I'll draw one here. So your Gaussian surface is like this. And then it's very easy to get the total charge inside this thing because it's uniform. It's the charge density times just the volume of that cylinder. Okay. So that's no problem at all. Outside, you'll actually find, so r less than radius, r greater than radius. So outside, you're going to find that it's got the same 1 over r dependence that we had for the simple line charge. Okay. Good. So these are very nice, and we've discussed them. Let's see what we have for 61 and 62. Oh, 62 is great. Electric field, total charge on Earth's surface. So 62 is just a Gauss's law for our entire Earth. Actually not difficult, but interesting. 61, conducting spherical shell. Yeah, so 61 is also pretty standard. So you've got a conducting spherical shell. So you've got hollow, and then you've got conducting material here. So inner radius, outer radius. And you're going to put some charge right at the middle. What do they want? Positive charge. Point charge, yeah, plus Q. Or they just say Q, doesn't matter. Okay. Point charge right at the center. And then you're going to use Gauss's law to find out what happens all the way out to this radius, on the other side, all the way out, and basically you're going to find out what the charge densities are, the surface charge densities at these interfaces here. Okay, and you have the full symmetry of the situation. You have Gauss's law, very basic. After all, remember, inside here, no field. Therefore, no net charge inside. If you've got Q here, you're going to have your minus Q distributed on the surface there and so forth. Okay, so that's a good problem. And I think I also already discussed number 73. So I think you'll enjoy these. Okay, that was the Bohr atom model, hydrogen atom model, not the Bohr model, but the hydrogen atom model. That was number 73. Okay, good. Enjoy these, and we'll see you guys next time.